Not sure.
Okay, we spent some time on Newton, I think last time around.
Yeah, second law.
Okay, Newton
And we
2.
did.
Okay, there's a definition that you will get. Otherwise, your Newton 2 definition is something that you'll have to learn off by heart. It's basically this: when a net force is or unbalanced force is applied to an object, it will accelerate in that direction, blah, blah, blah. You'll have to learn that. That's something you will get. And then what we did, we did some examples where we got a drawing or something, and then we did a free body diagram, and then we worked out the acceleration.
Yeah.
You remember this?
Yeah.
Okay, let me just pop through those examples. We also worked with kinetic friction, or coefficient of kinetic friction. Then we worked with tension in a rope of these two bodies, but we didn't do any examples here. This was just a free body diagram.
Yeah.
Did you now do any examples? Okay, this one we can delete. It's not. Did you do any examples like this where you worked out the acceleration of the system yet or not?
No, we just did the normal acceleration, free force direction.
Okay, so we did this, no acceleration. We did something like this. We worked out the acceleration. Remember this?
Yeah.
Okay, so where are you in school at the moment? Or in your...
So over the weekend, I went over the Newton's law 1.
Okay.
And then I just did the activities in my textbook.
On Newton 1.
Newton 1 and then some of Newton 2.
Okay, do you have any questions?
No, not actually.
Okay, then what we're going to do, we're going to do some more examples. Newton 1, you need to just understand what inertia is. There's a definition for inertia and there's need some explanation to be done. Okay.
Okay.
Right. You're going to go through those notes, and if you have any questions, then you can ask me. Right. So we're going to start back here with an example like, no, let's just start with an easy example. Right. So I've got a flat surface again, and there's a coefficient of kinetic energy of 0.145. And there's a block, and it weighs 8 kg. And I'm going to pull this just with a horizontal force of, let's say, 30 newtons. Right. Okay, easy. Then we're going to get an angle on that force, and then we're going to add a block or something. We're just going to build it up. So the first thing that you need to do, you need to be able to draw a free body diagram of all the forces on the 8 kg block. And that free body diagram sort of solve any question. It's like a visual reference to the sum. It's like a visual aid to solve the questions. Okay, so the first thing is what?
Arrow going up.
Arrow going up, it's called, okay, I can't draw a straight arrow up. For some or other reason, it's just not working. Okay, let me try that arrow. Bang. Okay, that's better. And that's normal. Fn, or just N for normal force. Next one.
We have one going to the right, which will be a force.
Yeah, the force or the applied force doesn't matter. It's just F, or Fa for applied. Yes.
And one going to the left for friction.
Okay. You're allowed to use F for friction or F_K for kinetic friction. We'll soon learn the difference between kinetic and static friction. And then?
Okay. And then one going down, Fg.
G force. Okay, that one. Fg. Good. That's very important. And those are also free marks. There's a lot of
Do
shear.
we have to put like 30 Newton and stuff on this diagram, or do we just leave it like that?
You can choose. Whenever you doubt, then you can do this. F applied force. In other words, you can add a label. But once you add a label to it, then you can basically call that everything you want to. You can make it like a smiley, and your label can be smiley. No, I'm just joking. You can't do that. But what I'm saying, if you doubt, then you can give it a label. But what you'll find, Amira, once you start working out papers with memos, then you'll see, oh, this is, they do it every time. They just do F. And then you get confidence in your answer. Okay, now, I want to know, number 2, what is the frictional force? They can ask you the force of friction, kinetic friction, or friction on the block. What is the force of friction, frictional force on the block? How do we do that? Equation, is that right?
Yeah.
Kinetic friction is the coefficient times the normal force. So now you can look on your diagram and see that the normal force and the FG force, they are in equilibrium. So they are the same. You have to set up a little equation for that, saying that the sum of the normal force and the FG force is 0. If I add those two forces, I get 0. So therefore, the normal force equals the mg force. What happened is this one was positive and the gravitational force was, say, for instance, negative. So if I take it over, it becomes positive. But you don't have to show that step. And then you can decide, do you want to calculate mg here? Or do you just want to, do you want to calculate mg? Or do you just want to use it in the next sum? So in other words, I can just say the frictional force is 0.15 times mg and then do the calculation here. The mass is 8 and the gravitation is 9.8. Or you could have calculated it and then use n in there. I just feel this is easier for now. It's quicker also. Otherwise you do extra calculations. Doesn't matter. It's what you feel comfortable with. What do we have there? 11.76 newtons to the left. Okay, make sure you've got that. And then you're going to talk about the acceleration of the block. Just make sure you've got that.
Okay, I got that.
Okay, talk to me about the acceleration. If I ask now, okay, what is the acceleration? What acceleration of the block?
And there's the Newton law to the F net equals to ma.
You have to write that. F net equals ma. Awesome. And then you have to look at the forces diagram. Those two forces are parallel to the surface or in line with the surface area. So the sum of those two forces will be ma. Let's make the frictional force 0 and the applied force positive because they're in different directions. So I'm just going to do this. The applied force plus negative friction force is the mass of the block times acceleration. So we have 30 minus 11.76 equals 8a. Still have that 11.76 in my calculator, so I just do 30 minus answer and then divide that with 8. 2.28. 2.28 meters per second square to the right. Was that easy?
Yeah.
Okay, now the thing is, this whole sum actually becomes much more difficult if that force is applied at an angle. So I'm just going to do the same. Everything is the same, but look at the difference here. Still going to have 30 newtons, but I'm going to take this force and apply it to an angle. I'll show you what happens now. Okay, I'm applying that to an angle of, let's say, make it easy, 60 degrees. Why? My forces diagram is slightly different now. I still have a normal force. I still have gravitation. I still have friction in this direction. But now I've got a force in that direction at an angle. So it's best to use the Fy and Fx components of that force. There's your applied forces X component, and there's your applied force Y component. You happy with that?
Yeah.
If you write a test or exam, I want you to do the following. If you used this diagram, just check the memo. Check, make sure that they've given you all the marks. If they haven't given you all the marks, you complain and I'll take it. I'll speak to the right person. I'll get you the marks. Okay. Because I have seen them not marking this as if they've never seen it. I don't know.
Okay.
I'm actually shocked. Anyway, it doesn't matter. The reason we're doing this is because now we can actually see that the normal force and the Y component together equals the FG component. So if the first question or the second question is, what is the force of friction? Then your equation will look like this. The kinetic friction is still the coefficient times the normal force, but now the normal force plus the Y component is the FG force. That makes a huge difference. Because I'm pulling at an angle, I'm also pulling up. I'm actually lifting, trying to lift the block from the floor. That means that the force that the floor exerts back onto the block is less. If you start lifting something from the floor slightly, not so that it leviates, it's just so that there's a force trying to pull it up, then the ground or the surface won't push as hard up against the object because you're countering the gravitational force. So now my normal force equals my Fg, which is mg minus the Y component. So the normal force is 8 times 9,8, it's less. And what is the Y component? Can you remember? Sin or cos?
Cos. I mean sin.
It's the force times sin of the angle. And then I can type into my calculator if that's too much to just transfer into a new sum. I have a calculator. Okay, that's 52, what? Wow, that's a lot actually. 52,41, no, it's less than 23 Newton. So my normal force, I'm going to plug it in there as an answer. It's 0,15. Although I'm going to write 52,419, I'm just going to use the answer in the calculator. You get that?
Yeah.
So I'm just going to do the answer times 0.15. Now the frictional force is less. 7,86 Newton to the left. Nice. Okay, so this is a much bigger sum. It's more marks too. And if you didn't draw that free body diagram, you would have probably worked it out. The normal force is the same as the FG, and then everything else is stuffed up and wrong. Have you done any examples like this in your textbook?
Yeah. Yeah. I did 2 of them.
Okay, but now look at this. The acceleration. What is the acceleration of the system? Well, F net, without writing that, you're losing marks, equals ma. So now the net force is the X component plus a negative frictional component. And that is 8a. Now the X component is cos. It's this. The force cos 60 minus 7,86, and that is 8a. Right. That is 15 minus answer. So 7,137 equals 8a. And the acceleration is 0,89 meters per second squared to the right. So interesting. If you take 30 newtons and you put it at an angle of 60 degrees, the block only accelerates at 0,89. What was our other acceleration? If you pull it horizontal in line with the floor, it was over 2,2 meters per second square. It's a huge difference. So if you've got a cupboard in your room and you're trying, you put a blanket underneath. I don't know if you've done it. You take a blanket underneath the cupboard. If you have a loose cupboard and you can't move it, it's too heavy. You tilt it, so you slide a blanket underneath it, and then you can pull it with a blanket. So you must never try and pull it at an angle. Always try and pull it flat to the surface. It's much easier. Even though you're lifting it from the floor, you've got your horizontal component of your force is always much more. Good. If you can do this, then we can move on to 2 blocks.
Yeah, we can do that.
You haven't done that yet.
No.
Okay, so now I've got this block again. Let's say it's 5 kg. I'm going to give you the frictional force. It's 10 newtons. Now I've got a pulley system. This is a frictionless pulley with a rope. It's called T for tension in the rope. And there's a weight there of, let's say, 2 kg. So I'm holding that system. Flat surface, 5 kg block. I'm giving you the frictional force. I'm making it easy. Then there's a rope attached to that block over frictional, no friction here, no friction in that pulley. And then there's another weight of 2 kg attached, or mass of 2 kg attached to that rope. So I'm going to leave it and it's going to accelerate in this direction. Okay, now free body diagram of both of them. Just take a piece of paper and just do a free body diagram, or just direct me what I need to do, because it's not difficult. This is easy free bodies to draw.
For the 5 kg, it will be normal going up.
Yeah.
Tension to the right.
Good.
To the left will be friction.
And FG.
And FG.
Okay, you're going to use a ruler and do it nicer. And then to the 2 kg, I only have the tension in the rope upwards. No.
Yeah. And then FG going down.
Okay, good. So this is the 2 kg and the 5 kg. Now, they want to know what is the tension in the rope. Okay, there's a way to do it. You need to solve both of these 2 equations simultaneously. So I have to set up a F-res or F-net equals MA for the 5 kg. And I have to set up a F-net equals MA for the 2 kg. Why? The tension in the rope is the same for both. And then that's going to be like the subject of the equation. So in the 5 kg, I have negative frictional force to the left. I have tension in the rope, which is positive, and that equals 5A. Are you happy with that?
Yeah.
I looked at those 2 forces. And the tension was positive because I'm choosing this direction around as positive. Right, so negative friction, negative 10, plus tension in the rope is 5A. So the tension in the rope is 5A plus 10, and there's my first equation. And then for the 2 kg, the tension in the rope will be negative because it's going up and back. So with regards to the 2 kg, the tension is going in a different direction, so it's negative. And my FG force is downwards, which is positive, and that is 2A. So I have negative tension plus MA equals 2a. I'm making tension the subject of the equation. It is 2 times 9,8. Oh, sorry, that's mg minus 2a. And that's the tension in a rope. Just see that you got that equation because I didn't write very neatly.
Yeah, no, I got it.
Okay, so now tension in a rope is the subject of both equations. So I'm just going to make 5a plus 10, or therefore, equal to 2 times 9,8 minus 2a. 7a equals 2 times 9,8, which is 19,6 minus 10 is 9,6. Don't do that in the exam, just work it out with a calculator and divide by 7. And then I get 1,37. A is 1,37 meter per second square. What? I don't need that as an answer because that's not asked. So they want to know the tension in a rope. Therefore, tension, I can use any one of these two equations. I'm going to use the easy one. Is 5 times A, which is 1,37. I'm not going to use 1,37. I'm going to use the answer. That is 1 4 something. And that is plus 10. Times 5 equals plus 10. And that is 16,86. The tension in a rope is 16,86 meters. And tension in a rope doesn't have direction because they've got different views of angles from which you can view it. Okay, not difficult. Okay, that's not difficult. I want to quickly just add something here. Just make sure that you get some work to do. And then I want to just run through it. See if you can do that. Assessment tests. Let's just also make sure that I don't need to. Just want to make sure that you can actually read this. Okay, I'm gonna send it to you via WhatsApp, and then I'm also gonna make sure that that you can see it on the screen now. Okay, just the next page. Easy ones. Just give me a second. Okay, this is Afrikaans. I don't know if you. Okay, so look at this. This is homework. So what is important on the homework? There's an ID there, 686, 868, 868. So there's a drawing of a 10 kg block with a force of 80 newtons and at a 60-degree angle. And then they tell us that there's friction there of 20 newtons. So the frictional force is 20 Newton. And then they're going to ask which of those diagrams are incorrect. Would you say any of those diagrams are incorrect? Which one is the first one is incorrect? No, the first one is correct. You see that it's got the applied force, it's got the normal force, it's got the weight component and the friction. Then the second one is also correct. The applied force is just divided into its components. Then what about number 3?
I think number 3 is the incorrect one.
No, it doesn't have a normal force.
Yeah.
So 3 is incorrect. What about 4?
No, 4 has one.
Number 4 is also incorrect. The friction is in the same direction as the applied force, which is wrong. You can't have
Yeah.
friction in this direction and a force applied in that direction. So that one's also wrong. So the answer is C, which is 3 and 4. Then what does this word mean? Hmm?
I have no clue.
What I'm doing, I'm just testing your English, really. If you don't know what that word is, then your your Afrikaans is quite bad. Then.
Yeah.
So I need to actually get this thing translated for you. No, it's unfair. I mean, if you don't know what versnelling is, it's acceleration, then you're gonna suffer. Okay, so what I'll do is I'll translate this for you and send it to you again. Okay, Amira. Hello.
Yeah, me.
Yeah, I know I couldn't
Oh,
hear you.
okay.
Now I'm just saying
Oh,
your Afrikaans is not on a very high level.
no, it's not.
It doesn't matter because you have to do physics here, not Afrikaans. But what I'll do is I'll just translate it and send it to you. Okay.
Okay, thank you.
So what I'll do is I am going to give you a login for this program. It's going to be in Afrikaans, the login. In other words, it's not a problem. There's nothing to read. I'm just going to give you the same test, the 868 code, but I'm going to do this in English for you. So what you're going to do, I'll show you how to do it next time on the program. Okay. So it's not a problem. You're going to have exactly the same test. The wording is just going to be in English. So that you everything is going to be the same. The wording is just English. Right. Good.
Yeah.
Okay. So I'm going to fix this in English and send it to you. Okay. We have to do one more thing. I have to explain something to you. Right. So there's a block. It's on the surface again. And it weighs 10 kg. Someone is putting in this direction with 30 newtons. And they're going to give you Fs. So this block is static. Fs means there's a static force of friction, not moving. Therefore, your acceleration is 0. If the acceleration is 0, then F net is also 0. Why? Because F net equals mass times acceleration. And if the acceleration is 0, the net force is also 0. So our free body diagram looks like this. Same, normal, applied force, static friction, and Fg. Can you tell me what the static friction is? Yes, it's 30 newtons. Why? Because F net is 0. Then the force applied plus negative friction will be 0. So the force that is applied equals the static friction. So 30 equals Fs. Static friction is 30 newtons to the left. That easy? Yes. If something is not moving and a force is applied to that, then something is pushing it back or holding it back. And that force must be exactly the same. Now, let's start again. This is kind of, you do understand this. It's not a problem, isn't it?
Yeah.
Let's start again. New block. It's 10 kg again. Now someone is attaching a rope there and start pulling it. But they gonna not immediately apply a 10 or a 20 Newton force. They're gonna slightly increase the force. So they're just gonna pull softly onto the rope and then they're gonna exert a bigger force, a bigger force, a bigger force. So we're gonna draw like a graph showing the force applied and the frictional force. So if you apply 1 Newton here and it's static, 1 Newton and static. Then the frictional force will also be 1 Newton. Do you agree?
Yeah.
So the frictional force will grow as you apply. Okay, now I'm going to apply like 8 Newton. Then the frictional force will also be 8 Newton. So they will, the frictional force and the force applied will be directly proportional to one another. The more force you apply, the more friction. And then suddenly it will drop. And it will look something like that. So what happens here? This is this part here, that part there, is what is called Fs max. That is the maximum static friction. And after that, this will be your kinetic friction. So what happens if you zoom into the surface with a microscope, then the bottom of the block looks like this. It's not perfectly flat, nor is the table or the surface that the block lies on perfectly flat. So if we zoom in, then you'll find that there's little irregularities in the surface. And these irregularities or jagged edges hook into one another. So now you can start pulling to the one side. And those surface areas, they hook into one another, which makes it very difficult to move. You can start pulling, pulling, pulling. And then suddenly at a certain force, let's say 30 newtons, those hooks are overcome. And once this object moves, it has got less friction. There is less friction once the object starts moving. So therefore, your kinetic friction is always lower than the maximum static friction. Always lower. Okay. So I don't know if you've moved a big object before. If you like, have you moved your bed or something in your room, or your cupboard, or your whatever desk? You've done that. You slide it over the surface.
Yeah, slightly to the other side.
Yeah. So what happens is initially to get it moving is difficult. You have to like pull it. But once it's moving, then it's easier to move it around because there's less friction on this object once it is moving than once it's static. Okay. Do you understand that?
Yeah.
It's got to do with Newton 1, inertia. An object doesn't want to move. If it's in rest, it doesn't want to move. Right. So let's do something with this. I'm gonna give you something and you can think, you can work on it for a couple of minutes. This is now a sloped surface. And we have a 5 kg block there. Okay. And this is at rest. So it's not moving. Good. So you can write there Fs, it's got static friction on it. And let's make this angle nice and easy, a 30-degree angle. I want you to do two things. One, I want you to do a free body diagram. So you're not gonna show me what to do now. You're gonna redraw this and draw a free body diagram. And two, I want you to figure out what is the force of static friction on the block. I want you to figure out what is, remember, you're not doing anything. A free body diagram is doing everything. I'm back in a couple of minutes. Tell you when I'm back, but I want you to, on your own, draw a free body diagram and think about how you're going to determine the static friction. I'm actually back in the app. How are you doing?
Okay, I guess. I did the
Okay, I
free
guess.
body diagram,
I've
but
got normal force there. I've got
yeah, I did like it
frictional
looks like a
force there.
cross.
Static. Oh, okay, static. Then I've got this is what they probably have in one of the memos, something like FG. But you can convert that. So this is correct. This is 100% correct. Okay.
I actually did the one that looks like a cross.
Yeah, that's a better one. So you draw the one with the normal force, the frictional static. Then you converted this FG component into FG parallel and FG perpendicular component. That's a better
Yeah.
one, but they're both 100% correct. Don't draw both, eh? Just draw one.
Okay.
If you do both, then you'll lose the marks. Okay, let's delete that one. Use this one. Okay, now this diagram is showing me the following. It's showing me that the static friction and the FG parallel component is the same. Why? Because the block is not sliding down or up. Those two are in equilibrium. So I have to start off with saying F net is 0 because it's in rest. Then FG parallel plus a negative Fs component is 0 because those are the two forces, two net forces. So the parallel component is the static friction component. They're the same. FG parallel is mg sin alpha, isn't it?
Yeah.
Okay, very good. So now I have mass, I think it was 5 or something. 5 times 9,8 sin 30 is the frictional static force. Good. Now what? 5 times 9.8 times 0.5. And that's 24,5. Up or slope up, up slope. Did you get that?
Yeah.
Okay, difficult question number 3. What is the coefficient of static friction? There's 2 ways of doing it. Easy peasy way and a difficult one. See what you can do there. Remember, this chapter or the method they want you to use is all about the following. It's all about reading your free body diagram and working from there. So I'm going to give you 3 minutes again.
Can you please show me how to do this?
Okay, 2 minutes. We need this. We need the free body diagram. Okay, this is more advanced now. And I mean, you're doing really well. Well, I'm not managing how to copy that. Okay, there we go. Okay, right. There's 2 ways of doing this. Important. If it's static, there are no external forces. So no one's pushing it. So no one's pulling. It's not static and someone is pulling a rope on it. Then you can just say that the mu s value, I don't think this red is quite cool. Let's just use a black. The coefficient of static friction is tan theta or alpha. So that's tan of 30 degrees. I'll show you now why. Tan 30, and that is 0,58. Okay, this is the method 1. And I wouldn't recommend that really because that you have to remember that and you feel sort of insecure. The best way is to say, look at this. The coefficient, so this is method 2. The coefficient of static friction is what? Oh, let's use the formula first. Let's use a formula first, otherwise we lose marks. So the static friction is the coefficient of static times the normal force. Okay. So look at this. We've got the static friction. But I'm not going to give you, I'm going to use this part of the equation. I'm just going to pull it in here. Look at this. What is the static friction? It is mg sin alpha times the coefficient. What is the normal force? Well, the normal force is the same as the Fg perpendicular force. The Fg perpendicular force is mg cos alpha. So that is mg cos alpha. So if I divide that away, I'm actually dividing mg sin alpha with mg cos alpha, and that is mu s mg, and sin divided by cos is tan. But you probably won't see this happening. Why? You will have the frictional force done already by now. So I'm going to just take this and make it smaller. This is where the method 1 comes from. So you'll probably just do this. You'll say that the frictional force is the coefficient of static frictions times the normal force. And then you say, I've got the static friction. It's 24,5 mu s. And the normal force is Fg perpendicular. So 24,5 is the coefficient times mg cos 30. And then you're going to divide it away, not even knowing that you're getting tan along the way. So 24,5 is mu s times 5 times 9,8 cos 30. And then if you divide that away, you'll get 0,58. And there's no unit for coefficient. It's just a value. Okay. This is new. So this is going to be new for you. If you look at your textbook, how many pages do you reckon you have left of the Newton 2 section? Take a guess. You don't have to be specific. I just want to know where you are at the moment.
Let's say about 5 pages.
5 pages. You've done a lot, eh? That's a lot of work you've done. Very proud of you, actually.
It ends at exercise 6. I'm on experiment 6.
What is the experiment all about?
So it's basically just like an exercise,
Okay.
but it is like hypothesis.
Okay. Good. Yeah, we'll do another one. Right. So this free body diagram is important. So I've got another 20-degree angle there. I've got a block. And I don't know its mass. And the friction is 8 Newton. And someone is exerting a force there on this block of, let's say, 20 Newtons. Can I give you the friction then? I don't know. I probably can. Okay, let's try that. Free body diagram. Okay, I know you can do this. So I have a normal force. Then I have applied force. Then I have friction and what? I have friction in this direction, kinetic. And I have Fg parallel now. And then I have Fg perpendicular. Is that correct?
Yeah.
Okay. I want to know, what is the mass? What's the mass of that object? Well, let's say it's accelerating upwards at 1 meter per second square. Okay, very important. You're not going to solve this. You're going to say F net equals MA. So you're not solving. This is what they did in this with the whole idea of the free body diagram, so that you're not really solving the sum. You allowing the sum to solve itself. So you're going to say, okay, fine, the net forces, let's choose the upward section as positive. So the applied force plus negative friction plus negative FG parallel equals MA. Is that correct?
Yeah.
If the upward force is positive, then those two components are negative. So now I have 20 newtons minus friction, 8. Minus, what's FG parallel? It is M, I don't have M, I don't have mass, times G times sin 20. And that is the mass times the acceleration upwards, which is 1. So, look, this was a difficult sum. I didn't know the mass, and this is the first time they're asking the mass. So let's just work that out. I've got 20 minus 8, which is 12, minus the mass I don't have, 9,8. Sin 20. I don't know what that is. I'm just going to write sin 20. Then I can type it in a calculator. And that is 1 mass. So I'm just going to throw that part over to the other side of the equation. So 12 equals 1 mass, which is just 1, plus 9.8 times sin 20. And then I get 4,3519 M. So now I'm just taking 12 divided with the answer. So it's 2,76. The mass is 2,76 kg. And this is a difficult sum. Why? It's a funny one. It's not normal. It's not standard. But the equation can still solve. Happy with that?
Yeah.
Okay, I think that's what we don't need to do anything else than that today. Next week, I want to finish the Newton 2 stuff with your questions and do some Newton 3 examples. So what is Newton 3? Let's just talk about it. We've got like 5 minutes to talk about it. What is Newton 3? It's action-reaction forces. In other words, if there's a wall there, and someone's pushing in that direction with 50 newtons, then there's an opposite force in the different direction of 50 newtons also. That force is opposed, pushed back with the same force, just in a different direction. So you are going to be probably busy with that next week when we start. Okay, I want to show you something. I'm going to stop the recording. So I want to show you something, what I want you to do